December 12, 2025. Across the northern hemisphere, millions of people looked up at a sky transformed by light. From New York to London, from Tokyo to Moscow, from rural farmlands to bustling cities, the Geminid meteor shower painted streaks across the darkness. In North America, observers counted more than 100 meteors per hour at the peak. European skywatchers reported brilliant fireballs bright enough to cast shadows on the ground. Asian observers documented colors, greens, blues, and occasional oranges, flashing briefly before fading. It was one of the most spectacular meteor displays in recent memory. People gathered in fields, on rooftops, in parks, anywhere they could escape the glow of city lights. Children pointed excitedly at each streak, asking questions their parents struggled to answer. Photographers captured long exposures showing dozens of trails converging from a single point in the constellation Gemini. For a few hours, the world paused to watch the cosmos put on a show. But here is what most of those observers did not know. What they were witnessing was not what they thought it was. For more than a century, we have told ourselves a simple story about meteor showers. Comets traveling through the solar system leave trails of debris behind them. When Earth's orbit crosses these trails, the particles enter our atmosphere and burn up. The friction creates the streaks of light we call shooting stars. It is an elegant explanation, one that has satisfied astronomers and the public alike. Schools teach it, textbooks repeat it, and planetariums present it as settled science. But recent discoveries have revealed that this story is incomplete. In some cases, it is entirely wrong. The meteors people watched on December 11, 2021, were not behaving the way traditional models predicted. Their velocities were slightly off, their chemical signatures unusual, and their arrival patterns showed anomalies that did not fit. Scientists noticed these discrepancies years ago, but dismissed them as measurement errors. Equipment glitches, atmospheric effects, or statistical noise. But as detection technology improved, the anomalies became impossible to ignore. Advanced camera networks, spectrometers, and radar systems began revealing details about meteors that previous generations could never have measured. Each meteor that burns up in our atmosphere leaves behind a chemical fingerprint. By analyzing the light it produces, scientists can determine what elements it contains. Iron, magnesium, sodium, silicon, all revealed in the brief flash before the particle disintegrates. For decades, these signatures matched what we expected from cometary debris. But starting around 2018, researchers began finding meteors with compositions that did not match their supposed parent comets. The differences were subtle at first, slight variations in isotope ratios or unexpected trace elements. But as more data accumulated, patterns emerged that challenged fundamental assumptions about where these objects come from. Dr. Peter Jeniskins at NASA's Ames Research Center was among the first to publish findings about these anomalies. His team analyzed thousands of meteor spectra collected by automated camera networks across California. What they found was surprising. A significant percentage of meteors in well-known showers like the Perseids and Geminids showed chemical compositions inconsistent with their supposed parent bodies. The isotope ratios suggested these particles did not form in our solar system's familiar regions. Some contained elements that typically form only in specific stellar environments. Others showed signs of having experienced conditions that do not exist anywhere in the inner solar system. The discovery raised immediate questions. If these meteors are not coming from the comets we thought they were, where are they coming from? How do they end up in streams that coincide with Earth's orbit? And what does this mean for our understanding of how the solar system works? The answers researchers are discovering are far more complex than anyone anticipated. Meteor showers are not just local phenomena created by nearby comets. They are windows into processes that span the solar system and potentially beyond. Each streak of light carries information about cosmic events, some recent, others ancient. Materials from different regions of space, mixed together in ways we are only beginning to understand. This realization is transforming how astronomers study meteors. What was once considered a well-understood field is becoming a frontier of discovery. New instruments are being deployed, new theories proposed, and new questions asked about what these cosmic visitors can tell us. Tonight, we will explore what scientists have recently learned about meteor showers. Not through speculation or imagination, but through careful observation and rigorous analysis. We will look at the technology that makes these discoveries possible, the surprising origins some meteors have revealed, and what these findings tell us about the solar system's history and structure. This is not a story about mysterious forces or exotic theories. It is a story about science, revealing nature's complexity one measurement at a time. About researchers following data wherever it leads, even when it contradicts long-held beliefs. And about the universe showing us that even familiar phenomena can hold surprises. So settle in, let your mind drift among the stars, and prepare to see meteor showers in a completely new light. Because what we thought we knew about these cosmic light shows is only the beginning of the story. Welcome to Info Jungle. If you enjoy calm, thoughtful explorations of science and space, consider subscribing. We create these documentaries to help you learn and relax at the same time. Let the story unfold naturally as we journey into the mysteries revealed by meteor showers. Before we can understand what scientists have recently discovered, we need to establish what meteor showers are. Not the simplified version taught in schools, but the more nuanced reality that observations have revealed. This foundation will help us appreciate just how surprising the new findings truly are. A meteor shower occurs when Earth passes through a stream of particles orbiting the Sun. These particles, most no larger than grains of sand, collide with our atmosphere at tremendous speeds. The friction generates heat that vaporizes the particle and ionizes the surrounding air. This process creates the brief streak of light we see as a shooting star. The term meteor refers specifically to the light phenomenon, not the particle itself. The particle is called a meteoroid while it travels through space. If any piece survives to reach the ground, it becomes a meteorite. Most meteoroids that create meteor showers are too small to survive atmospheric entry. They burn up completely at altitudes between 80 and 120 kilometers above Earth's surface. The entire event typically lasts less than a second. Despite their brevity, meteors release considerable energy. A meteoroid the size of a pebble, traveling at 60 kilometers per second, carries kinetic energy equivalent to a small explosive. When this energy converts to heat and light, it creates a flash visible from hundreds of kilometers away. Meteor showers are called showers because many meteors appear to radiate from a single point in the sky. This point is called the radiant, and showers are named after the constellation where their radiant is located. The Perseids radiate from Perseus, the Geminids from Gemini, and so on. But the meteors do not actually come from those constellations. The radiant is an optical illusion created by perspective. The meteoroids are actually traveling on parallel paths through space. When Earth moves through this stream, the particles enter our atmosphere from the same direction. From our viewpoint on the ground, these parallel paths appear to converge at a distant point, just like parallel railroad tracks appear to meet at the horizon. This creates the illusion that all the meteors are streaming from a single location. Understanding this geometry helps astronomers trace meteor streams back to their sources. By measuring the radiant position precisely and analyzing meteor velocities, researchers can calculate the orbital paths of the meteoroids. This tells them where in the solar system the particles came from and how long they have been orbiting the Sun. For most major meteor showers, these calculations point to specific comets. The Perseid meteor shower, visible every August, is associated with comet Swift-Tuttle. The Orionids in October come from comet Halley. The Geminids in December are linked to an object called 3200 Phaethon, which is classified as an asteroid, but behaves somewhat like a comet. These associations were established through careful observation over many years. When a comet approaches the Sun, solar heating causes ices on its surface to sublimate. This creates the characteristic tail and coma, the glowing atmosphere surrounding the nucleus. But the heating also releases dust and small rocky particles embedded in the ice. These particles are pushed away from the comet by solar radiation pressure and the solar wind. Over time, they spread out along the comet's orbital path, forming a debris stream. If Earth's orbit intersects this stream, we experience a meteor shower. The timing is predictable because both Earth and the debris stream follow stable orbits around the Sun. Each year, Earth returns to approximately the same position at approximately the same date. If that position crosses a meteor stream, we see a shower at that time every year. This regularity is why meteor showers are annual events with predictable peak dates. However, the intensity can vary significantly from year to year. The density of particles in a meteor stream is not uniform. Some regions are denser than others, creating stronger or weaker displays depending on which part Earth passes through. Occasionally, Earth crosses a particularly dense filament, producing a meteor storm with thousands of meteors per hour. The Leonid meteor storm of 1966 produced rates estimated at 150,000 meteors per hour at its peak. More commonly, major showers produce rates between 50 and 100 meteors per hour under ideal conditions. Ideal conditions mean dark skies away from light pollution, clear weather, and the radiant high in the sky. Urban light pollution dramatically reduces the number of visible meteors. Under city skies, observers might see only a fraction of the meteors visible from rural locations. The moon's phase also affects visibility. A bright moon near full illuminates the sky and washes out fainter meteors. The best meteor viewing happens during new moon periods when the sky is darkest. Meteor showers occur throughout the year, but some are more prominent than others. The major annual showers include the Quadrantids in early January, the Lyrids in April, the Eta Aquariids in May, the Perseids in August, the Orionids in October, the Leonids in November, and the Geminids in December. Each has characteristics that distinguish it from the others. Perseid meteors tend to be bright and fast, often leaving persistent trails called trains that glow for several seconds. Geminid meteors are slower and often show colors, particularly green from magnesium and blue from iron. These differences reflect variations in the composition and velocity of the meteoroids. Faster meteors burn brighter because friction increases with velocity. The square of the velocity determines kinetic energy, so doubling speed quadruples the energy released. Composition affects color through a process called emission spectroscopy. Different elements emit light at specific wavelengths when heated. Sodium produces orange, magnesium creates green, and ionized calcium contributes violet. By photographing meteor spectra, scientists can determine what elements the meteoroid contained. This technique has become increasingly sophisticated with modern instruments. Automated camera networks now capture high-resolution spectra of hundreds of meteors every night. The data reveals not just elemental composition, but isotopic ratios that provide clues about where and how the material formed. This brings us to the recent discoveries that are changing our understanding. Because when scientists began analyzing these detailed spectra, they found something unexpected. The compositions did not always match what the associated comets should produce. In some cases, the differences were dramatic enough to suggest the meteors came from entirely different sources. This realization has opened a new chapter in meteor science, one that is still being written. Understanding what meteor showers are helps us appreciate why the recent discoveries are so significant. When the fundamental assumptions about meteor origins are called into question, the entire field must adapt. New technology has made this questioning possible, revealing details invisible to previous generations. For centuries, watching meteor showers required nothing more than dark skies and patience. Observers would count meteors, note their brightness, and perhaps sketch their paths. The data collected was valuable but limited. Without instruments to measure velocity, composition, or precise trajectory, many questions remained unanswered. The 20th century brought improvements. Photography allowed meteors to be captured on film, providing permanent records of their appearance. Multiple cameras at different locations could photograph the same meteor, enabling triangulation to determine altitude and trajectory. Radar systems detected meteor trails by bouncing radio waves off the ionized gas left behind. This worked even in daylight, revealing meteor showers that were invisible to optical observation. But these methods had limitations. Photography required long exposures and caught only the brightest meteors. Radar provided trajectory data, but no information about composition. Neither technique could capture the detailed spectra needed to analyze chemical makeup. The 21st century changed everything. Digital cameras with high sensitivity replaced film. Computer processing allowed real-time analysis of meteor data. And networks of automated stations began operating continuously, capturing meteors that would previously have gone unrecorded. These technological advances have transformed meteor science from occasional observation to continuous monitoring. Let us look at the tools making new discoveries possible. Modern meteor detection combines multiple technologies working together. Cameras, spectrometers, radar, and even satellites contribute to a comprehensive picture. Understanding these tools helps us appreciate the reliability of the discoveries they enable. The backbone of modern meteor observation is the automated camera network. Organizations like NASA's All-Sky Camera Network and the European Meteor Network operate hundreds of cameras across multiple continents. Each camera watches a large section of sky continuously throughout the night. When software detects a meteor, the system automatically records it and extracts key data. Position, time, brightness, color, and trajectory are all calculated within seconds. These networks capture tens of thousands of meteors every year. The data goes into databases accessible to researchers worldwide, enabling statistical analysis that would have been impossible before. But cameras alone cannot reveal everything about meteors. For composition analysis, specialized instruments called spectrographs are needed. A spectrograph splits light into its component wavelengths, creating a spectrum that shows which elements are present. When a meteor burns, different elements emit light at characteristic wavelengths. By identifying these wavelengths, scientists determine what the meteoroid contained. Modern meteor spectrographs use diffraction gratings to split light with high resolution. They are often paired with cameras in automated stations. When a camera detects a bright meteor, the spectrograph simultaneously captures its spectrum. The combination provides both visual data and chemical analysis of the same event. Radar adds another dimension to meteor observation. Unlike cameras, radar works in all weather conditions and during daylight. It detects meteors by bouncing radio waves off the ionized trails they create. The reflected signal reveals the meteor's velocity, trajectory, and altitude. Radar is particularly valuable for detecting meteor showers that occur during daylight hours, when optical observation is impossible. The Arietid shower in June is one such example. Its radiant rises with the sun, making visual observation nearly impossible. But radar stations detect it clearly, revealing it to be one of the strongest annual showers. Radar also detects smaller meteors than cameras typically capture. Very faint meteors, invisible to the eye and most cameras, still create enough ionization to reflect radar signals. This extends meteor monitoring to particles much smaller than those studied through optical methods. Satellites contribute another layer of observation. Some weather satellites carry instruments sensitive to the infrared flashes produced when large meteoroids explode in the atmosphere. These events, called bolides or fireballs, release tremendous energy visible from space. Satellite data has revealed that Earth is hit by surprisingly large meteoroids more frequently than previously thought. Several meter-sized objects enter the atmosphere each year, though most explode harmlessly at high altitude. The combination of ground-based and space-based observation creates a comprehensive monitoring system. But collecting data is only the first step. Analysis requires sophisticated software and considerable computational power. Automated systems process incoming meteor observations in real time. They calculate trajectories, determine orbits, and flag unusual events for human review. Machine learning algorithms are increasingly used to identify patterns in large datasets. These systems can detect subtle anomalies that might escape human notice. For example, slight variations in meteor shower timing that might indicate gravitational effects from Jupiter or other planets. The software can also group meteors by orbital similarity, identifying streams that might not be recognized through casual observation. One particularly important analysis technique is called orbital determination. By combining trajectory data with velocity measurements, scientists can calculate the meteoroid's orbit before it hit Earth. This reveals where in the solar system the particle came from. For shower meteors, the orbits typically cluster around the orbit of the parent comet. But recent analysis has found meteors in known showers with orbits that do not match the expected pattern. Some meteors in the Geminids shower, for instance, have orbital elements suggesting they did not come from Phaethon. Instead, they appear to originate from regions of space far from where Phaethon's debris should be. Similarly, some Perseid meteors show orbital characteristics inconsistent with Swift-Tuttle. These anomalies are what first alerted scientists that something unexpected was happening. The technology exists to measure these differences precisely. But understanding what they mean requires looking more carefully at where meteors actually come from. Advanced instruments reveal that meteor streams are more complex than traditional models suggested. Not all particles in a shower come from the same source. Understanding this requires examining the various ways meteoroids can enter Earth-crossing orbits. The instruments watch, the cameras capture, the data streams back to Earth. Every meteor leaves a story written in light and chemistry. Scientists have spent decades building networks to catch these stories. Now, those networks reveal something unexpected. Meteor showers are not what we thought they were. The Perseids appear each August, reliable, predictable, consistent. For centuries, astronomers assumed each shower came from one source. One comet, one trail of debris, one stream through space. But high-resolution tracking changed that understanding completely. In 2018, researchers analyzed thousands of Perseid meteors. They measured the exact trajectory of each one. They calculated where each meteor came from in space. The data revealed multiple paths, multiple origins, multiple streams. The Perseids weren't one shower, they were several showers overlapping. This discovery changed everything scientists thought about meteor streams. It opened questions that had never been asked before. Where do these multiple streams come from? How do they form? How do they evolve? The answers would reshape our understanding of the solar system. The comet Swift-Tuttle created the Perseid meteor shower. Or at least, that's what astronomers believed for over a century. Swift-Tuttle orbits the Sun every 133 years. Each orbit, it sheds dust and ice into space. That debris forms a trail that Earth passes through each August. But modern tracking revealed something more complex. The Perseid stream contains at least 3 distinct components. Each component has a slightly different orbital path. Each arrives at Earth from a slightly different direction. This shouldn't be possible if they all came from one comet pass. Scientists call these components filaments. Filaments are narrow streams within the larger meteor stream. Each filament represents debris from a different comet passage. Swift-Tuttle has orbited the Sun for thousands of years. Each orbit created a new trail of debris. Those trails don't stay in the same place. Gravity tugs on them, solar radiation pushes them. Over centuries, they spread out along Swift-Tuttle's orbital path. But they don't spread evenly, they cluster into filaments. Each filament maintains its own identity through space. Earth encounters different filaments at different times. Sometimes we pass through a dense, young filament. Those years bring spectacular meteor outbursts. Sometimes we pass through older, dispersed debris. Those years bring normal shower activity. The 1993 Perseid outburst demonstrated this perfectly. Observers counted over 300 meteors per hour that year. 3 times the normal rate for the Perseids. Scientists realized Earth had passed through a dense filament. That filament contained debris from Swift-Tuttle's 1862 passage. Tracking these filaments requires incredible precision. Researchers calculate the orbit of thousands of individual meteors. They look for clusters of similar orbits in the data. Each cluster represents a distinct filament in the stream. The work is painstaking. The results are revolutionary. The Leonids show even more dramatic filament structure. Comet Tempel-Tuttle creates the Leonid meteor shower. Tempel-Tuttle orbits the Sun every 33 years. Most years, the Leonids produce modest meteor rates. But every 33 years, something spectacular happens. Earth encounters the densest part of the Leonid stream. The sky fills with thousands of meteors per hour. These events are called meteor storms. They occur when Earth passes through recent debris trails. The debris hasn't had time to spread out yet. In 1833, observers witnessed an incredible Leonid storm. Estimates suggest 100,000 meteors per hour fell that night. People describe the sky as filled with falling stars. Some thought the world was ending. Scientists realized something extraordinary was happening. The 1866 Leonid storm was almost as intense. Then the storm stopped. Decades passed with modest shower rates. The pattern repeated in 1966 with another major storm. Then 1999, then 2001, each separated by about 33 years. The pattern matched Tempel-Tuttle's orbital period perfectly. Modern modeling explains this pattern clearly. Each time Tempel-Tuttle orbits the Sun, it sheds fresh debris. That debris forms a narrow, dense trail behind the comet. If Earth's orbit intersects that fresh trail, we see a storm. If we miss the fresh trail, we see only background activity. But here's where it gets complex. Scientists discovered that Leonid storms aren't just one trail. They're multiple trails from different comet passages. The 1999 storm came from debris trails laid down in 1899 and 1866. The 2001 storm came from 1767 trail material. This means debris trails can persist for centuries. They maintain their structure through hundreds of orbits around the Sun. Gravity from Jupiter and Saturn affects these trails over time. The trails shift, they drift, they evolve. But they don't disappear, they don't completely disperse. Researchers use computer model to track these ancient trails. They input the comet's orbital history going back centuries. They simulate how debris spreads from each passage. They calculate where those debris trails are today. Then they compare predictions to actual meteor observations. The match is remarkable. Models predict outbursts years in advance. In 1999, scientists predicted a Leonid storm within hours of when it occurred. This wasn't luck. It was detailed understanding of filament dynamics. It proved that meteor streams are complex, structured objects. Each stream tells a story that spans centuries. The Geminids show another variation of this pattern. Comet Geminids creates the Draconid meteor shower. The shower usually produces only a handful of meteors per hour. But occasionally, the Draconids explode into intense activity. These outbursts are brief but spectacular. In 2011, observers saw 300 Draconid meteors per hour. The outburst lasted only a few hours. Scientists realized Earth had crossed a very narrow filament. That filament was only about 30,000 kilometers wide. For context, Earth's diameter is about 12,700 kilometers. The precision required to predict such encounters is staggering. Scientists must know Earth's position to within thousands of kilometers. They must know the filament's location to the same precision. They must calculate gravitational effects from every planet. Even small errors mean missing the prediction entirely. Yet modern astronomy achieves this precision regularly. Space missions provide exact planetary positions. Radar and optical tracking give precise meteor velocities. Computer models simulate millions of dust particle orbits. The result is an intricate map of the solar system's dust streams. This map reveals something profound. Every major meteor shower consists of multiple components. Some components are ancient, spread thin by time. Others are recent, still dense and concentrated. Earth passes through this complex structure each year. The Geminids demonstrate this in unexpected ways. Unlike most showers, the Geminids come from an asteroid, not a comet. The asteroid Phaethon orbits very close to the Sun. Solar heating may cause Phaethon to shed dust particles. Those particles form the Geminid stream we encounter each December. Recent observations show the Geminid stream has multiple peaks. Earth encounters different density regions on consecutive nights. Some years show enhanced activity on December 13th. Other years peak on December 14th or 15th. This variability suggests multiple dust trails in the stream. Scientists believe Phaethon has been active for thousands of years. Each close approach to the Sun might release fresh material. That material adds new filaments to the existing stream. Over time, these filaments spread and overlap. The result is a complex, layered structure. Understanding filament structure has practical implications. Spacecraft traveling through the solar system encounter meteor streams. Dense filaments pose collision risks for satellites and missions. Knowing where filaments exist allows mission planners to avoid them. It's another example of pure science enabling practical applications. The discovery of multiple stream components solved old mysteries. Why do some meteor showers vary in intensity from year to year? We're passing through different filaments with different densities. Why do outbursts occur at seemingly random intervals? We're encountering ancient debris trails that models now predict. Each filament carries information about its parent body. The dust composition reflects the comet's interior chemistry. The orbital path reveals gravitational influences over time. The density tells us how much material the comet shed. Every meteor becomes a messenger from the ancient solar system. Scientists continue mapping these filaments in greater detail. New camera networks track fainter meteors than ever before. Satellite observations provide data from above Earth's atmosphere. Each observation adds to our understanding of stream structure. The picture grows clearer with every passing year. What seemed simple a century ago is now wonderfully complex. Meteor showers aren't singular streams from single sources. They're braided rivers of dust flowing through space. Each braid tells its own story. Each has its own history. Together, they reveal the dynamic nature of our solar system. The streams flow through space, multiple trails, multiple origins. But streams are made of individual particles, billions upon billions of dust grains. Each grain is unique. Each has traveled its own path. What are these particles made of? Where do they come from? For decades, scientists could only speculate about dust composition. Meteors burn up too quickly to analyze directly. They vaporize in the atmosphere within seconds. Their light provides clues, but not complete answers. Then researchers found a new way to study meteor dust. High-altitude aircraft can fly above most of the atmosphere. They carry sticky collector plates that capture cosmic dust. These particles drift down slowly after meteors vaporize. The dust is microscopic, barely visible, incredibly precious. Each grain contains information about the early solar system. Scientists examine these particles in laboratories. They use electron microscopes to see their structure. They use mass spectrometers to identify their chemistry. The results reveal unexpected diversity among meteor dust. Not all dust is created equal. Not all comes from the same place. Interplanetary dust fills the space between planets. The amount is staggering. Thousands of tons fall to Earth annually. Most particles are smaller than grains of sand. They come from comets, asteroids, and even interstellar space. Each source contributes differently to the cosmic dust budget. Cometary dust makes up most meteor shower particles. When comets approach the sun, their ice sublimates. Gas jets carry dust particles away from the nucleus. Those particles enter independent orbits around the sun. Over time, they spread along the comet's orbital path. But not all cometary dust is the same. Different comets produce different types of dust. Some comets are rich in silicate minerals. Others contain more carbon-based organic compounds. The differences reflect conditions where the comets formed. Scientists collect dust from meteor showers throughout the year. Each shower provides samples from a different parent comet. Perseid dust comes from Swift-Tuttle. Leonid dust comes from Tempel-Tuttle. Gemini dust comes from asteroid Phaethon. Laboratory analysis reveals each shower has a unique signature. Perseid particles tend to be fragile and rich in organic material. They crumble easily under examination. This suggests they formed from loosely bound comet material. The particles haven't been heavily processed by solar radiation. Leonid particles show different characteristics. They're often harder and more compact than Perseid dust. They contain more crystalline silicates. These minerals form at higher temperatures. This tells us something about Tempel-Tuttle's formation history. Geminid particles are stranger still. They're extremely fragile, even more so than typical comet dust. Yet they come from an asteroid, not a comet. This paradox puzzled scientists for years. How can asteroid debris be more fragile than comet dust? The answer lies in Phaethon's unusual orbit. Phaethon approaches closer to the Sun than any other named asteroid. At closest approach, surface temperatures exceed 800 degrees Celsius. This extreme heating may cause rocks to crack and fracture. Thermal stress breaks apart the surface layer. The resulting particles are like crushed stone. They're rocky material that's been shattered by temperature cycling. This process creates dust very different from cometary ice sublimation. It's mechanical destruction rather than chemical release. The result is fragile, irregular particles. Scientists discovered another surprising source of meteor dust. Some particles don't match any known comet or asteroid composition. They contain isotope ratios not found in solar system bodies. This suggests an origin outside our solar system entirely. These are interstellar dust particles. Interstellar dust drifts through the galaxy constantly. Our solar system moves through this galactic environment. Some interstellar particles enter our planetary system. They mix with local cometary and asteroidal dust. Occasionally, they appear in meteor shower samples. Identifying interstellar particles requires careful analysis. Researchers look for unusual isotope signatures. Isotopes are variants of elements with different neutron counts. Different stellar processes create different isotope ratios. Particles from other star systems have recognizable alien signatures. The first confirmed interstellar dust particles were found in 1996. They came from samples collected by high-altitude aircraft. The particles contained unusual oxygen and nitrogen isotopes. The ratios couldn't be explained by solar system processes. The only explanation was formation around distant stars. Since then, scientists have identified dozens of interstellar grains. They're rare, Only about 1 in 100,000 particles is interstellar. But their presence reveals galactic connections. Material from distant stars mingles with our local dust. The solar system isn't isolated. It's part of a larger cosmic ecosystem. Understanding dust composition helps solve other mysteries. Why are some meteor showers more colorful than others? Different elements produce different colored light when they vaporize. Sodium produces yellow, magnesium produces blue-green. Iron produces orange, calcium produces violet. The Perseid meteors often show colorful trails. This indicates their dust contains diverse elements. The variety reflects the chemical complexity of Swift-Tuttle's nucleus. Different regions of the comet contribute different compositions. We see this diversity played out in meteor colors. The Leonid meteors are often green. This suggests high magnesium content in Tempel-Tuttle's dust. Magnesium is common in silicate minerals. The green color tells us about mineral composition. It's chemical analysis happening at meteor velocities. Spectrographic analysis takes this further. Spectrographs spread meteor light into its component wavelengths. Each element produces characteristic spectral lines. By measuring these lines, scientists identify elements present. It's like doing chemistry at 60 kilometers per second. Modern spectrograph networks capture hundreds of meteor spectra annually. The data reveals patterns across different meteor showers. Some showers consistently show strong sodium lines. Others show abundant iron or calcium. Each pattern reflects the parent body's composition. But there's a complication. Meteor spectra don't exactly match parent body composition. The vaporization process isn't uniform. Some elements vaporize at lower temperatures than others. This creates observational biases in spectral data. Scientists account for these biases through careful modeling. They simulate how different elements vaporize in meteor conditions. They calculate which elements should appear brightest. Then they compare simulations to observations. The process reveals true compositional differences between showers. These differences teach us about comet formation. Comets formed in the outer solar system over 4 billion years ago. Different regions had different temperatures and compositions. Comets from the Kuiper Belt differ from Oort cloud comets. Their dust reflects these primordial differences. The dust also records later processing. Cosmic rays bombard particles as they orbit the sun. Solar radiation alters surface chemistry. Micrometeorite impacts modify grain structures. Each particle carries a history of space weathering. Scientists can sometimes read this history. They examine impact craters on collected dust grains. They measure radiation damage in crystal structures. They analyze chemical alteration layers. Each feature reveals time spent in space. Some particles show minimal space weathering. These are young particles, recently released from their parent body. Other particles show extensive modification. These are ancient, possibly orbiting for thousands of years. The age distribution tells us about stream evolution. Fresh streams contain mostly young particles. Ancient streams contain more weathered material. By analyzing dust age, scientists estimate stream ages. This connects to the filament structure discovered earlier. Different filaments contain particles of different ages. The complexity extends to particle size distribution. Meteor streams contain particles ranging from molecules to pebbles. Most are sand-sized or smaller, but the exact size distribution varies between streams. This variation affects how streams evolve over time. Smaller particles respond more strongly to radiation pressure. Sunlight actually pushes tiny particles outward. This effect, called radiation pressure, acts like a gentle wind. It slowly moves small particles away from the sun. Over time, this separates small particles from large ones. Larger particles respond more to gravitational forces. They're less affected by radiation pressure. They stay closer to the parent body's orbital path. This creates size sorting within meteor streams. Different Earth encounters sample different size populations. Scientists observed this during the 2009 Perseid shower. Early in the shower, meteors were predominantly small. Later in the shower, average meteor size increased. This indicated Earth was passing through sorted regions of the stream. The observation confirmed theoretical predictions about size distribution. Understanding dust complexity has practical importance. Spacecraft traveling through the inner solar system encounter this dust. Even tiny particles pose risks at orbital velocities. Impact speeds can exceed 20 kilometers per second. At those speeds, microscopic particles hit like bullets. Space agencies design shielding based on dust environment models. They need to know particle sizes, densities, and velocities. They need to predict encounter rates for mission planning. Meteor science provides this critical data. It helps protect multi-million-dollar spacecraft. The complexity also affects Earth in subtle ways. Interplanetary dust reflects and scatters sunlight. This creates the zodiacal light visible from dark locations. It's a faint glow along the ecliptic plane. Ancient astronomers noticed it, but didn't understand its cause. Now we know it's scattered sunlight from dust clouds. These clouds are densest along the ecliptic. That's where most comets and asteroids orbit. The light reveals the distribution of dust in space. It's a visible map of interplanetary matter. Scientists use zodiacal light observations to study dust globally. Ground-based telescopes measure its brightness and distribution. Space telescopes observe it without atmospheric interference. The data reveals dust cloud structure throughout the inner solar system. It's a complement to meteor observations from Earth. Together, these approaches paint a comprehensive picture. Interplanetary dust is diverse, complex, and dynamic. It comes from multiple sources with different properties. It evolves through radiation, gravity, and collisional processes. Each particle tells a story spanning millions of years. The dust particles carry stories, chemical signatures, historical records. But chemistry alone doesn't explain everything about meteor showers. Scientists discovered unexpected elements in meteor spectra. Materials that shouldn't be there based on comet models. Something about dust composition challenged fundamental assumptions. The surprises began with sodium. Sodium is common in meteor spectra. It produces the distinctive yellow color in bright fireballs. Scientists expected sodium. They found something else too. They found amounts of sodium that didn't make sense. Comets are made mostly of ice and rock. Simple models predicted modest sodium content. But observations showed abundant sodium in many meteors. Far more than models could explain. Where was all this sodium coming from? The sodium mystery emerged gradually over decades. Early meteor spectroscopy showed strong sodium emission lines. Scientists noted this, but couldn't measure precise abundances. Modern spectrographs changed that situation. They revealed sodium was extremely abundant in meteor vapor. In some meteors, Sodium appeared more abundant than expected by tenfold. This wasn't a minor discrepancy. It was a major anomaly. Comets shouldn't contain that much sodium. Chemical models of comet formation couldn't explain it. Something about the models was wrong. Researchers proposed several explanations. Perhaps sodium concentrated on dust-grained surfaces. Maybe comets formed from sodium-rich building blocks. Or possibly, sodium came from elsewhere entirely. Each hypothesis needed testing. Laboratory experiments provided crucial insights. Scientists created synthetic comet materials in labs. They subjected these materials to simulated solar heating. They measured what elements released first. Sodium was among the most volatile elements. This meant sodium would escape easily from comet surfaces. Solar heating would drive sodium away before other elements. Dust particles leaving comets might be sodium depleted. This made the high sodium observations even more puzzling. Particles should have less sodium, not more. The breakthrough came from studying dust collection samples. Scientists analyzed particles collected by high-altitude aircraft. They used sensitive instruments to map elemental distributions. What they found surprised everyone. Sodium wasn't evenly distributed in dust particles. Instead, sodium concentrated in tiny inclusions. These were microscopic pockets within larger dust grains. The inclusions were rich in sodium-bearing minerals. When meteors vaporized, these pockets released sodium suddenly. This created the strong sodium emission lines. But why did these inclusions exist? The answer relates to how dust forms around comets. Comets contain various ice types, not just water ice. Carbon dioxide ice, carbon monoxide ice, and other volatiles exist too. Each ice type vaporizes at different temperatures. As comets approach the sun, ices sublimate in sequence. Water ice sublimates, releasing dust particles. But some dust particles contain trapped volatile ices. These ices remain frozen inside the dust. They survive the initial release from the comet. Later, as dust particles orbit closer to the sun, these ices sublimate. They leave tiny voids where ice once existed. Other volatile materials concentrate in these spaces. Sodium compounds accumulate in these microscopic pockets. The result is sodium-rich inclusions in otherwise normal dust. This discovery explained the sodium mystery beautifully. It also revealed something profound about dust structure. Dust particles aren't homogeneous. They're complex assemblages with varied compositions. They contain materials from different formation environments. The sodium discovery opened questions about other elements. Scientists looked more carefully at meteor spectral data. They found other compositional surprises. Iron appeared in unusual forms. Calcium showed unexpected abundance patterns. Iron normally exists in metallic or oxidized forms. In meteor spectra, scientists detected unusual iron compounds. Some meteors showed iron sulfides. Others showed organic iron complexes. These compounds suggested complex chemistry in comet dust. Iron sulfides form under reducing conditions. This means oxygen was scarce during their formation. Such conditions existed in the early solar nebula. Finding these compounds in meteor dust was remarkable. It meant some dust preserves primitive solar system chemistry. Scientists call these materials presolar grains. They formed before the solar system existed. They survived incorporation into comets and asteroids. Now they appear in meteor showers. They're messengers from before our sun ignited. Identifying prosolar grains requires isotope analysis. Different stellar processes create different isotope ratios. Our Sun creates characteristic solar system isotope patterns. Prosolar grains have different patterns from other stars. These alien isotope signatures are unmistakable. Researchers found prosolar grains in collected meteor dust. The grains contained silicon carbide and graphite. They showed isotope ratios from red giant stars. These stars lived and died before our solar system formed. Their dust became part of the molecular cloud that created the Sun. The percentage of prosolar material is tiny. Maybe 1 grain in 10,000 is prosolar. But their presence demonstrates incredible preservation. These grains survived solar system formation. They endured billions of years in comet interiors. Now they vaporize in Earth's atmosphere as meteors. Scientists capture that brief flash of light. They analyze the spectrum, seeing elements from dead stars. It's a connection spanning billions of years. It's cosmic recycling on the grandest scale. Organic compounds provided another compositional surprise. Many meteors show emission lines from carbon molecules. These aren't simple carbon compounds. They're complex organic molecules with multiple carbon atoms. Some are the building blocks of life. Scientists detected cyanide compounds in meteor spectra. They found carbon chains with nitrogen attached. They observed aromatic hydrocarbons. These molecules are common in interstellar space. Finding them in meteors confirms comets carry organic material. This has implications for life's origin on Earth. Early Earth was bombarded by comets and asteroids. If those bodies carried organic compounds, they delivered them here. Life's building blocks may have arrived from space. Meteor showers demonstrate this delivery continues today. The organic molecules appear in varying amounts. Some meteor showers show strong organic signatures. Others show primarily mineral compositions. This variation reflects differences between parent bodies. Some comets are more organic-rich than others. The Perseid meteors show particularly strong organic features. Swift-Tuttle apparently contains abundant organic material. The Leonids show less organic content. Tempel-Tuttle seems more mineral-dominated. These differences teach us about comet diversity. Scientists discovered amino acids in collected meteor dust. Amino acids are the building blocks of proteins. They're essential for life as we know it. Finding them in space suggests they're common throughout the universe. Life's chemistry may be universal, not unique to Earth. The amino acids found in meteor dust are unusual. They include forms not used by Earth life. Earth organisms use left-handed amino acids exclusively. Space amino acids include both left and right-handed forms. This proves they formed in space, not from Earth contamination. Water presented another compositional puzzle. Comets contain water ice. Everyone knew this. But the isotopic composition of comet water was controversial. Some comets had water matching Earth's oceans. Others had very different isotope ratios. Scientists measure the ratio of deuterium to hydrogen. Deuterium is hydrogen with an extra neutron. Different formation temperatures create different deuterium ratios. Cold formation environments produce high deuterium ratios. Warmer environments produce lower ratios. Earth's ocean water has a specific deuterium ratio. For comets to have delivered Earth's water, they need matching ratios. Early measurements suggested most comets had wrong ratios. Their water was too deuterium-rich. This challenged the idea that comets brought Earth's water. Then scientists measured water in Jupiter family comets. These are comets from the Kuiper Belt region. Their water had deuterium ratios closer to Earth's oceans. This suggested Jupiter family comets might have delivered our water. It reopened the question of Earth's ocean origins. Meteor science contributes to this debate indirectly. Scientists can't directly measure water in meteors. Meteors vaporize too quickly for water detection. But they can measure other volatile compounds. These provide clues about parent body composition. Hydroxyl radicals appear in some meteor spectra. Hydroxyl forms when water breaks apart. Finding hydroxyl suggests water-bearing minerals in dust. The amount and frequency of hydroxyl detections vary. This indicates variable water content in different meteor streams. Phosphorus provided yet another surprise. Phosphorus is essential for life. It's a key component of DNA and cell membranes. Scientists didn't expect to find much phosphorus in meteor spectra. Phosphorus emission lines are difficult to detect. Advanced spectrographs changed this. They detected phosphorus in multiple meteor showers. The amounts were small but measurable. This meant comets deliver phosphorus to Earth. It's another life-essential element arriving from space. The phosphorus likely exists as phosphate minerals. These minerals form in the presence of water. Finding them suggests aqueous chemistry in comet interiors. Water and minerals reacted together inside comets. This created complex chemistry we're only beginning to understand. Scientists realized comets aren't simple dirty snowballs. That old model is far too simplistic. Comets are complex chemical factories. They contain diverse minerals, organics, ices, and prosolar grains. Each comet is unique, with its own compositional signature. Meteor showers reveal this diversity continuously. Each shower samples a different parent body. Each parent body tells a different story. Together, they reveal the chemical variety of the outer solar system. They show us the materials that built planets. The compositional discoveries continue. New instruments detect fainter emission lines. Better calibration improves abundance measurements. Each improvement reveals new details about meteor chemistry. The field advances rapidly with technology. Scientists now compile databases of meteor compositions. Thousands of spectra from dozens of meteor showers. The data shows patterns and outliers. It connects meteor chemistry to parent body origins. It reveals the solar system's chemical story. The chemistry tells stories, origins, evolution, connections. But chemistry isn't destiny for meteor streams. Something else shapes how streams evolve over time. Something pushes and pulls dust through space. Gravity, the invisible hand sculpting the solar system. Meteor streams don't orbit in isolation. They travel through a solar system full of massive planets. Jupiter, Saturn, even Earth itself create gravitational fields. These fields tug on passing dust particles. Over centuries, these tugs reshape entire meteor streams. Scientists noticed this when predictions started failing. Old meteor storm predictions assumed streams stayed constant. They calculated when Earth would encounter dense filaments. Sometimes predictions worked perfectly. Other times, storms failed to appear. The answer lay in gravitational perturbations. Planets don't just affect asteroids and comets. They affect everything orbiting the sun, including dust. Even tiny particles feel planetary gravity. Those forces accumulate over time. Jupiter dominates gravitational dynamics in the solar system. It's over 300 times more massive than Earth. Its gravity shapes the asteroid belt. It captures comets into short-period orbits. It also profoundly affects meteor streams. When a meteor stream passes near Jupiter, gravity alters particle orbits. Particles get pulled slightly toward the giant planet. Their velocities change, their orbital paths shift. The effect is small for a single passage, but streams encounter Jupiter repeatedly over centuries. Scientists model these encounters using computer simulations. They track millions of dust particles over thousands of years. They include gravitational effects from all major planets. The simulations reveal complex orbital evolution. Meteor streams don't remain static, they transform. The Leonid stream provides a clear example. Tempel-Tuttle orbits Jupiter's vicinity regularly. Jupiter's gravity affects the comet and its dust. Some Leonid particles get pulled into different orbits. Others get ejected from the stream entirely. This explains why Leonid storm predictions are difficult. The stream structure changes between each 33-year cycle. Material from older comet passages may be displaced. It might miss Earth even though calculations suggested an encounter. Jupiter's influence introduces uncertainty into predictions. Scientists discovered this through careful observation. The 1899 Leonid storm was intense. Predictions suggested the 1932 storm would also be strong. But 1932 brought disappointing meteor rates. Something had altered the stream. Detailed modeling showed Jupiter's effect. Between 1899 and 1932, the Leonid stream passed near Jupiter. The encounter shifted particle orbits slightly. The densest parts of the stream missed Earth in 1932. Jupiter had stolen our meteor storm. This realization changed meteor storm forecasting. Scientists now include planetary perturbations in models. They calculate not just where streams are, but where they'll be. They simulate gravitational evolution forward in time. The predictions have become more reliable. Saturn also influences meteor streams significantly. It's less massive than Jupiter, but still substantial. Streams passing near Saturn experience similar perturbations. The effect accumulates over multiple orbital periods. Eventually, Saturn can completely reshape a stream. The Perseid stream shows Saturn's influence. Computer models track Perseid particles backward in time. They reveal Saturn has affected the stream for millennia. Without Saturn, the Perseid stream would look different today. Its gravitational influence is woven into stream structure. Even Earth affects meteor streams. Earth is much smaller than Jupiter or Saturn. But meteor streams pass very close to our planet. At close range, even Earth's modest gravity matters. The effect is subtle but measurable. When a meteor stream encounters Earth, two things happen. First, particles near Earth get pulled slightly toward our planet. This increases the encounter velocity slightly. It concentrates particles in Earth's gravitational well. The effect enhances meteor rates during peak shower times. Second, Earth's gravity permanently alters some particle orbits. Particles passing very close to Earth get deflected. Their paths through space change slightly. Over many Earth encounters, this reshapes the stream. It's a slow process but relentless. Scientists discovered this effect through long-term meteor observations. They compared meteor shower rates over decades. Some showers showed gradual changes in peak times. The peaks shifted by minutes or hours per year. This indicated orbital evolution from Earth encounters. The Geminid shower demonstrates this clearly. Historical records show the Geminid peak has shifted. In the 1960s, the peak occurred on December 13th. By 2000, it had shifted to December 14th. By 2020, some years peaked on December 15th. This shift indicates the stream is evolving. Earth's repeated encounters nudge particle orbits forward. The stream gradually drifts later in December. Computer models confirm Earth's gravity causes this drift. It's measurable evidence of ongoing orbital evolution. Mars also affects some meteor streams. Mars is smaller than Earth, but has influenced certain streams. Streams crossing Mars's orbit feel its gravitational pull. The effect is modest, but accumulates over time. Some particles get diverted into Mars-crossing orbits. Scientists speculate about Martian meteor showers. If Earth experiences showers, Mars should too. Mars rovers haven't detected meteors directly yet. But future missions might observe Martian meteor activity. It would confirm streams affect multiple planets. Venus presents an interesting case. Venus is nearly Earth's size with similar gravity. Streams passing near Venus experience Earth-like perturbations. But Venus has no moon to stabilize its orbit. This makes Venusian encounters harder to predict precisely. The outer planets, Uranus and Neptune, matter less for most streams. They're far from the Sun, where few meteor streams exist. Their gravitational influence is negligible for inner solar system streams. But they affect streams from long-period comets. These streams originate in the distant Oort cloud. Long-period comet streams are particularly chaotic. The parent comets take thousands of years to orbit. During each orbit, they pass all the planets. Each planet perturbs the orbit slightly. The cumulative effect is profound. Scientists struggle to predict long-period comet stream encounters. The streams evolve rapidly compared to short-period streams. Ancient observations often don't help with modern predictions. The stream has changed too much. Only recent observations provide useful data. Gravitational resonances create additional complexity. Resonances occur when orbital periods have simple ratios. A particle orbiting twice while Jupiter orbits once is in one resonance. Resonances amplify gravitational effects over time. They can dramatically alter particle orbits. Some meteor stream particles enter resonances accidentally. Once in resonance, they experience enhanced perturbations. Their orbits evolve faster than non-resonant particles. Eventually, they may leave the stream entirely. Resonances slowly deplete meteor streams over millennia. The Taurid meteor complex shows resonance effects clearly. The Taurids are a broad, diffuse meteor stream. They're associated with Comet Encke and related asteroids. The stream shows evidence of multiple gravitational disruptions. Resonances with Jupiter have scattered material widely. Scientists identified multiple Taurid shower components. The northern Taurids peak in November. The southern Taurids peak slightly earlier. Beta Taurids appear in daylight hours. Each component represents material scattered by gravitational effects. The Taurid complex may be quite ancient. Some researchers suggest it formed thousands of years ago. A larger parent comet broke apart, perhaps from Jupiter's gravity. The fragments created the current complex of streams. The idea remains controversial but intriguing. Gravitational modeling helps test such hypotheses. Scientists simulate comet breakup under various conditions. They track how fragments and dust would evolve. They compare simulation to observed stream properties. Matches suggest possible formation scenarios. These models require enormous computational power. Tracking millions of particles over thousands of years demands fast computers. Modern supercomputers make such calculations feasible. Results help us understand not just current streams, but their history. We can reconstruct how streams looked centuries ago. This has practical applications for historical astronomy. Ancient observers recorded unusual meteor events. Chinese astronomers noted exceptional meteor displays. Medieval European chronicles mentioned stars falling like rain. Were these encounters with now dispersed streams? By modeling stream evolution backward in time, scientists can check. They calculate where streams were centuries ago. They determine if Earth would have encountered dense regions. Sometimes this confirms historical records. Other times, it reveals records were misinterpreted. The historical perspective reveals stream lifetimes. Meteor streams don't last forever. Gravitational perturbations eventually disperse them completely. Particles spread around their entire orbital path. The stream becomes undetectable as a discrete shower. Scientists estimate typical stream lifetimes. Young streams might last only a few thousand years. Older, well-established streams can persist for tens of thousands. But eventually, all streams fade into background sporadic meteors. Gravity ensures this inevitable dispersal. New streams form to replace old ones. Comets continually shed fresh material. New debris trails appear in the inner solar system. Eventually, Earth's orbit intersects these new streams. We observe them as novel meteor showers. Several new meteor showers have been discovered recently. The camelopardalids appeared in 2014. This shower came from comet 209P Linear. Earth encountered fresh debris from the comet's 18.031924 passages. The shower was brief but confirmed predictions. The discovery validated gravitational modeling techniques. Scientists predicted the shower years in advance. They calculated when Earth would cross comet debris trails. The prediction was accurate to within hours. It demonstrated our understanding of stream dynamics. Other new showers await discovery. Thousands of comets orbit the Sun. Many have never been connected to meteor streams yet. As camera networks expand, more associations will be found. Each new stream provides data about its parent comet. Gravitational effects extend beyond simple orbit changes. They influence how streams disperse over time. Particles with different sizes respond differently to gravity. Large particles follow tighter orbits than small ones. This size sorting segregates streams over time. Scientists observe this sorting in established streams. Early in a shower, smaller particles dominate. Later, larger particles become more common. The effect is subtle but measurable. It confirms theoretical prediction about size-dependent dynamics. The gravitational environment varies throughout the solar system. Near Jupiter, tidal forces are extreme. Dust particles can be stretched and disrupted. Near Earth, forces are gentler. Particles survive intact to become meteors. This explains why Jovian meteor streams are rare. Jupiter's gravity is so strong it disrupts streams quickly. Material from comets passing Jupiter gets scattered. It rarely forms coherent streams. The environment is too dynamically active. By contrast, the inner solar system allows stream formation. Gravitational perturbations are moderate. Streams can survive for millennia. Earth benefits from this relatively calm environment. It's why we experience predictable annual showers. Understanding gravitational effects required decades of work. Early astronomers lacked tools to model complex dynamics. They could predict simple orbits but not streams. Computers revolutionized meteor stream science. They made complex simulations possible. Modern models include all gravitational effects simultaneously. Sun, planets, relativistic corrections, everything. They track individual particles through complex force fields. The accuracy is remarkable. Predictions now routinely succeed where old methods failed. This understanding helps protect spacecraft too. Mission planners need to know about dust hazards. Gravitational models predict where dense streams exist. Spacecraft can avoid these regions. It's another practical benefit of fundamental research. The study of gravitational effects continues evolving. Scientists discover new resonances and dynamical pathways. They find unexpected connections between streams. Each discovery refines our understanding. The solar system's gravitational dance grows clearer. Gravity shapes the streams, planets perturb them, time disperses them. But where do streams come from in the first place? Every stream traces back to a parent body. A comet, an asteroid, something shedding dust. Yet some parent bodies remain mysterious. Scientists have connected dozens of meteor showers to specific comets. The matches are clear, orbits align, chemistry matches. But other showers remain orphans. Their parent bodies are unknown, lost, perhaps destroyed. These mysteries drive some of the most exciting research. Sometimes the parent body is right there, hiding in plain sight. The Geminids puzzled scientists for over a century. A major meteor shower with no known comet. Then astronomers found Phaethon, the strange asteroid. Its orbit matched, the mystery seemed solved. But questions remained. Asteroids don't normally shed dust like comets do. They're solid rock, not ice and dust. How could Phaethon create a major meteor shower? The answer would challenge assumptions about meteor parent bodies. The first meteor shower connected to a parent body was the Perseids. In 1862, astronomers discovered comet Swift-Tuttle. They calculated its orbit carefully. The orbit intersected Earth's path precisely where the Perseids appeared. The connection was undeniable. This discovery revolutionized meteor science. If the Perseids came from Swift-Tuttle, other showers had comets too. Astronomers began searching systematically. They calculated meteor stream orbits. They compared them to known comet orbits. The Leonids connected to comet Tempel-Tuttle in 1866. The Orionids linked to comet Halley. The Eta Aquarids also traced to Halley from a different part of Earth's orbit. One by one, showers found their parent comets. A pattern emerged. Most major meteor showers come from Jupiter family comets. These are comets with orbital periods under 20 years. Jupiter's gravity captured them from longer orbits. They orbit relatively close to the Sun. They shed dust frequently, creating dense streams. But some showers remain mysterious. The Geminids were the most perplexing. They're one of the strongest annual showers. Reliable, intense, visible from both hemispheres. Yet no comet matched their orbit. Astronomers searched for decades. They calculated precisely where the parent body should be. They scanned that region repeatedly. Nothing appeared. The parent body was missing. Perhaps it had disintegrated. Perhaps it was too faint to see. Then in 1983, the IRAS satellite detected something unusual. IRAS observed the sky in infrared wavelengths. It found a small asteroid in an odd orbit. The asteroid came very close to the Sun. Its orbit matched the Geminid meteor stream perfectly. Astronomers named the asteroid Phaethon. In Greek mythology, Phaethon drove the Sun's chariot too close to Earth. The name fit. Phaethon approached closer to the Sun than any named asteroid. At closest approach, it passed inside Mercury's orbit. Surface temperatures reached 800 degrees Celsius. But asteroids don't create meteor showers. At least that's what everyone believed. Asteroids are solid rock. They don't have ice to sublimate. Without ice sublimation, how could Phaethon shed dust? The discovery opened a new mystery. Observations provided some clues. Astronomers detected a faint dust tail near Phaethon during closest solar approach. The tail appeared only when Phaethon was closest to the Sun. This suggested solar heating, released material somehow. But the mechanism remained unclear. Several theories emerged. Perhaps Phaethon was a dead comet nucleus. All its ice sublimated long ago, leaving only rock. But thermal stress from extreme heating caused fracturing. Fractured material crumbled into dust. Laboratory experiments supported this idea. Scientists subjected meteorite samples to rapid heating cycles. The rocks cracked from thermal stress. Surface material flaked off in dust-sized fragments. The process could produce substantial dust over time. Another theory suggested desiccation cracking. Deep inside Phaethon, pockets of ice might remain. As the asteroid rotates, these pockets heat unevenly. Remaining ice sublimates, creating internal pressure. The pressure cracks the surface, releasing dust. Recent observations favor the thermal fracturing explanation. The dust released during solar approach appears rocky. It lacks the volatile ices seen in comet dust. Chemical analysis of Geminid meteors supports this. They're consistent with heated, fractured rock. But Phaethon's origin remains debated. Is it a dead comet, an unusual asteroid, something in between? Some evidence suggests it came from the main asteroid belt. Other evidence points to cometary origins. The truth might be a hybrid. Phaethon might represent a transition object. It could have started as an icy comet. Jupiter's gravity perturbed it into a sun-grazing orbit. Centuries of intense heating drove off all surface ice. What remains looks like an asteroid, but behaves partly like a comet. Scientists call these objects active asteroids. They're asteroids that somehow produce dust like comets. Phaethon was the first recognized example. Since then, others have been discovered. Each challenges simple comet versus asteroid classifications. The distinction between comets and asteroids blurs at small sizes. Both are remnants from solar system formation. Both contain similar materials in different proportions. An asteroid with a little ice can act like a comet. A comet that lost its ice looks like an asteroid. This realization changed how scientists classify small bodies. The old binary system, comet or asteroid, was too simple. Reality is more complex. Objects exist on a continuum. Phaethon sits somewhere in the middle. It's teaching us that nature resists neat categories. Other meteor showers have similarly mysterious parents. The quadrantids are another major shower. They appear each January with reliable intensity. The parent body is asteroid 2003 A1. But this object also has comet-like characteristics. 2003, A1 might be a fragment of a larger comet. Historical records describe a comet in 1490 that matches the orbit. Perhaps that comet broke apart. 2003, A1 could be the largest surviving piece. Smaller fragments created the quadrantid meteor stream. This fragmentation scenario appears in several cases. Comets can break apart from tidal stress near the Sun. They can fracture from collisions with other objects. They can split from rotational forces or internal pressure. Each fragment becomes a potential parent body. The Taurid complex illustrates this dramatically. Multiple asteroids and Comet Encke share similar orbits. They all contribute to the broad Taurid meteor stream. Scientists believe they're fragments of a much larger comet. That parent comet broke apart thousands of years ago. The fragments dispersed along their shared orbital path. Some remained large enough to see as asteroids or comets. Others shattered into dust, forming the meteor stream. The entire complex preserves evidence of catastrophic disruption. It's a cosmic crime scene waiting to be fully understood. Some meteor showers have no identified parent at all. The June Bootids appear sporadically. Most years bring only a few meteors per hour. Occasionally, rates surge dramatically. The parent body remains unidentified. This shower might come from a disrupted comet. The parent body may have broken apart completely. Nothing large remains to identify. Only the debris stream survives. It's a ghost shower from a vanished parent. Other showers show unusual characteristics, suggesting complex origins. The Perseids appear each December. They're linked to Comet Tuttle. But the stream is older than Tuttle's current orbital configuration. Gravitational perturbations changed Tuttle's orbit over time. The Perseid stream reflects Tuttle's ancient orbit. Material shed thousands of years ago still orbits the Sun. Earth encounters this ancient debris annually. It's a window into Tuttle's past configuration. The stream remembers history the comet has forgotten. Some parent bodies are comets we've visited with spacecraft. In 2014, the Rosetta mission reached Comet 67P/Churyumov-Gerasimenko. Rosetta observed the comet for 2 years. It watched dust release from the surface. It measured dust properties directly. The observations revealed complex dust release patterns. Dust emerged in jets from specific regions. Activity varied with solar heating and rotation. Different regions produced different dust types. The comet was heterogeneous, not uniform. This heterogeneity explains meteor shower variations. When Earth encounters different parts of a stream, we sample different source regions. Meteors reflect the comet's compositional diversity. Some meteors come from active jet regions. Others come from quieter surface areas. The Rosetta data helps interpret meteor observations. Scientists compare meteor spectra to Rosetta's measurements. They identify which comet regions contributed which meteors. It's like forensic science, matching evidence to sources. The combination of spacecraft data and meteor observations is powerful. Future missions will visit more comet parent bodies. Each mission provides ground truth for meteor studies. We'll better understand how comets shed dust. We'll connect meteor properties to specific comet processes. The field will advance dramatically with each mission. Some parent bodies surprise us with their nature. Asteroid Bennu was visited by NASA's OSIRIS-RX mission. The spacecraft observed Bennu ejecting particles from its surface. Small dust clouds puffed away sporadically. Bennu was active, like a weak comet. The mechanism remains uncertain. Perhaps meteorite impacts kicked up dust. Maybe thermal cracking released material. Possibly internal ice remained and sublimated occasionally. Whatever the cause, Bennu demonstrated asteroids can be active. This means more asteroids might have associated meteor streams. We've only identified showers from a few asteroids so far. Hundreds of near-Earth asteroids exist. Some might produce weak meteor showers. Finding them requires careful observation and analysis. The search for parent bodies continues. Advanced telescopes detect ever fainter objects. New asteroids and comets are discovered regularly. Each discovery might explain an orphan meteor shower. Each connection adds to our understanding. Sometimes showers appear from nowhere. New meteor activity appears with no prediction. Observers worldwide report unexpected meteors from a new radiant. Scientists scramble to calculate the stream's orbit. Then they search for the parent body. This happened with the 2016 Phoenix meteor shower. Observers detected unusual meteor activity from Phoenix constellation. The shower hadn't been predicted or observed before. Scientists calculated the stream's orbit quickly. They identified the parent, Comet Blancpain. Comet Blancpain was discovered in 1819, then lost. Astronomers rediscovered it in 2003. The comet had fragmented and faded dramatically. It shed material that Earth encountered in 2016. The meteor shower revealed the comet's recent activity. These discoveries demonstrate our knowledge remains incomplete. The solar system still holds surprises. New streams appear, parent bodies fragment, orbits evolve. Meteor science is not a finished field. It's an active, dynamic area of discovery. The parent body mysteries extend to interstellar meteors. In 2017, astronomers detected Oumuamua passing through the solar system. It was the first confirmed interstellar object. It showed unusual acceleration, suggesting outgassing. Could it shed dust that becomes interstellar meteors? Scientists calculated Oumuamua's trajectory backward. It came from the direction of the star Vega. But it didn't originate from Vega's system. Oumuamua traveled through interstellar space for millions of years. Its true parent system remains unknown. If Oumuamua shed dust, Earth might encounter it eventually. The dust would have unique properties. Interstellar velocities far exceed normal meteor speeds. Chemical composition would differ from solar system objects. Detection would prove interstellar material directly enters our atmosphere. Some researchers have searched for interstellar meteors already. They look for meteors with unusual velocities. They search for chemical signatures indicating extrasolar origin. So far, no confirmed detections exist. But the search continues. The parent body mysteries remind us of how much remains unknown. Every answer raises new questions. Every discovery reveals deeper complexity. Meteor showers bridge the gap between what we know and what we wonder. They keep science alive with curiosity. The parent bodies orbit, they shed dust, they create streams. Earth passes through, we see meteors, we learn. Each year the cycle repeats, the showers return. But science doesn't stand still, technology advances. The future promises discoveries we can barely imagine. Today's meteor science uses sophisticated instruments. Camera networks, spectrographs, radar systems, satellites. These tools transformed the field over recent decades. Yet even better instruments are coming. The next generation of technology waits in development labs. Scientists plan orbital observatories dedicated to meteor science. Space-based cameras will observe meteors from above. They'll see meteors over oceans and remote regions. They'll track meteors without atmospheric distortion. The data will be unprecedented in quality and coverage. New ground-based networks are expanding globally too. Cameras in developing regions fill observational gaps. Antarctica, Pacific Islands, Central Asia, all getting instrumentation. Soon, every meteor everywhere will have potential observers. The global network will become truly comprehensive. The future of meteor science rests on several foundations. Better instruments will capture more detailed data. Faster computers will model streams more accurately. Spacecraft missions will visit more parent bodies. All these advances are already beginning. The next generation of camera networks promises revolutionary capability. Current cameras capture meteors to about magnitude +3. That's roughly as bright as naked eye visibility. Next generation cameras will reach magnitude +6 or fainter. This increase doesn't sound dramatic, but it is. Each magnitude step represents 2.5 times more light. 3 magnitudes is about 16 times fainter. Going from +3 to +6 means detecting far more meteors, possibly 10 times as many meteors per night. The data volume will explode. This data explosion requires new analysis methods. Human observers can't process thousands of meteors nightly. Artificial intelligence will take over initial classification. Neural networks will identify meteors automatically. Humans will review interesting cases and outliers. AI is already being trained on existing meteor data. Systems learn to distinguish meteors from satellites. They recognize different meteor types by appearance. They calculate trajectories automatically. The accuracy improves continuously with more training data. Soon, AI might discover new meteor showers autonomously. The system would detect unusual radiant clustering. It would alert human scientists to investigate. New showers could be identified within hours of first appearance. The discovery process will accelerate dramatically. Spectrographic networks will expand significantly. Currently, only a few dozen spectrographs operate globally. Plans exist for hundreds of systems. Each system will be more sensitive than current instruments. Spectral resolution will improve too. Higher resolution spectra reveal more element emission lines. Rare elements like beryllium or scandium might become detectable. This would provide new constraints on parent body composition. It would test solar system formation theories. Each new element detected adds information. Some spectrographs will operate in infrared wavelengths. Infrared captures different emission lines than visible light. Certain molecules emit strongly in infrared. Organic compounds, for instance, show distinct infrared features. Infrared spectroscopy will reveal organic content more clearly. Radar systems are being upgraded worldwide. Current radar detects meteors but provides limited detail. Next-generation systems will measure Doppler shifts precisely. This reveals meteor velocity changes as they decelerate. Velocity profiles indicate meteor mass and density. Advanced radar will detect much smaller meteors. Current systems catch meteors down to about 1 millimeter size. New systems might reach 0.1 millimeter. These tiny particles carry information about dust production. They reveal how parent bodies shed their finest material. Satellite observations will become more common. Several space agencies plan meteor-observing missions. Small satellites in low Earth orbit can watch continuously. They'll observe meteors from space before atmospheric entry. This provides data impossible to get from the ground. Space-based observations reveal meteor altitudes accurately. Ground observers see meteors against the sky's background. Space observers see meteors against Earth's surface. Parallax from multiple satellites determines exact positions. This improves trajectory calculations significantly. One proposed mission would use formation-flying satellites. Multiple small satellites would observe meteors simultaneously. The combined observations would create 3D trajectory maps. Every meteor would be tracked through its entire atmospheric path. The detail would be extraordinary. Spacecraft visiting comets provide ground truth. The European Space Agency plans additional comet missions. NASA considers a comet sample return mission. Japan Space Agency, JAXA, explores comet flyby concepts. China announced interest in comet exploration. Each mission will observe dust release directly. We'll see how comets shed material in real time. We'll measure dust properties before atmospheric entry. Then we can compare to meteor observations back on Earth. The connection between source and observed meteor strengthens. Sample return missions offer the most exciting prospects. Collecting comet dust and returning it to Earth enables detailed analysis. Laboratories can use instruments impossible to send to space. They can study samples over months or years. The scientific return is enormous. NASA's Stardust mission demonstrated this approach. Stardust collected dust from Comet Wild 2 in 2004. The samples returned to Earth in 2006. Analysis continues today, nearly 2 decades later. Each study reveals new details about cometary material. Future sample return missions will collect more material. They'll visit different types of comets. They'll sample multiple regions of each comet's nucleus. The diversity of returned samples will teach us about comet variety. We'll understand why different meteor showers have different properties. Computer modeling advances rapidly. Current simulations track millions of particles. Future simulations will track billions. They'll include more physical processes. Radiation pressure, charging effects, even collisions between particles. These detailed simulations will reveal stream evolution precisely. Scientists will continue their work. They'll build better instruments. They'll refine their models. They'll discover new showers and solve old mysteries. Each generation adds to the collective understanding. The work never finishes. The questions never end. But for most people, meteor science is simpler. It's lying on a blanket under dark skies. It's waiting for that streak of light. It's the sudden thrill when one appears. That moment needs no explanation. The science enriches that moment without diminishing it. Knowing meteors are ancient comet dust doesn't make them less beautiful. Understanding orbital mechanics doesn't reduce the wonder. Knowledge and awe coexist perfectly. They enhance each other. So when you see a meteor, remember, you're watching a particle older than human civilization. It's traveled millions of kilometers to meet Earth. For one brief second, it illuminates our sky. Then it's gone, leaving only light and memory. That particle came from a comet that circled the sun for eons. It drifted through space in streams we're only beginning to map. Gravity shaped its path, Planets perturbed its orbit. Solar radiation pushed it. Time dispersed it. Yet somehow, impossibly, it found its way to your eyes. In that moment of light, science and beauty merge. The meteor is both cosmic messenger and fleeting art. It's both ancient history and present wonder. It's both physical process and transcendent experience. That duality is what makes meteor science so compelling. The universe speaks in many languages: mathematics, physics, chemistry, but also in beauty, in wonder, in moments of awe. Meteor showers teach us to listen in all these languages. They reward attention with insight. Perhaps that's why humans have always watched the skies. We're not content with simple survival. We need meaning. We crave understanding. The stars offer both, if we're patient enough to look. Meteors are the universe's gifts to the patient. Technology will advance, knowledge will grow, but the core experience remains human and simple. A dark sky, a meteor, a watcher. That triangle has existed for thousands of years. It will exist for thousands more. The scientists work to understand the mechanics. The poets work to capture the feeling. The rest of us simply watch and wonder. All three approaches are valid. All three matter. Together, they form our relationship with the cosmos. As you fall asleep tonight, meteors are falling somewhere. They're writing light across someone's sky. They're delivering ancient messages to modern eyes. They're connecting Earth to the greater solar system. The process is constant. The wonder is renewable. Tomorrow night, more meteors will fall. Some will be seen. Most will go unnoticed. But whether witnessed or not, they'll be there. The streams flow on. The sky continues its ancient show. We're invited to watch whenever we choose. That invitation never expires. The sky waits for everyone equally. Rich and poor, young and old, scientists and poets. Anyone can step outside and look up. Anyone can see what thousands of years of humans have seen. In our modern world, that connection to the past matters. We live in artificial light and controlled environments. We forget we're part of something larger. Meteors remind us the universe breaks through our isolation. Those streaks of light are cosmic punctuation marks. They mark the rhythm of Earth's journey through space. Each shower is a milestone in our annual orbit. The Perseids mean summer is ending. The Geminids announce winter's arrival. The sky keeps time in falling stars. And so the streams flow through space. Dust particles following ancient orbits, occasionally intersecting Earth's path, briefly illuminating, teaching, inspiring, then continuing on into the darkness. Scientists will study them, artists will celebrate them, children will wish on them, lovers will watch them together. Each person finds their own meaning in those fleeting lights. That's as it should be. That's as it's always been. The meteors don't mind. They simply fall. Rest now. Let sleep come gently. The sky continues its watch without you. The streams orbit, Earth moves, meteors fall. These ancient cycles need no witnesses to persist. But when you wake, they'll still be there, waiting for your attention, ready to inspire wonder, ready to teach anyone willing to look up, ready to connect us to the cosmos, ready to remind us we're part of something vast. The meteor showers continue. They always have, they always will. As long as comets orbit and Earth travels through space. As long as humans look upward with curious eyes. The story continues. The discovery never ends. Good night, sleep well. The universe watches over us all. In streams of ancient dust. in streaks of sudden light, in the patient turning of the cosmic wheels. Tomorrow the sun will rise. The meteors will fade into daylight, but they'll return when darkness falls. They always return, they always will. The sky promises this. The sky keeps its promises. Rest in that certainty. The universe is vast, but patterns persist. Chaos and order balance perfectly. The meteor showers prove this every year. Reliable, predictable, yet full of surprises. That's the final lesson of meteor science. The universe is knowable, but never fully known. We can predict, but cannot control. We can understand, but always remain humble. The meteors fall, teaching these truths to anyone watching. Close your eyes now. Let the knowledge settle into dreams. Streams of dust orbiting in darkness. Planets pulling, gravity shaping, time flowing. All moving in elegant cosmic choreography. You are part of that dance. Earth carries you through the streams. The atmosphere protects you from the dust. But your mind can travel anywhere. Through streams, through space, through time. Science is that journey. Understanding is the destination that never arrives. Wonder is the fuel that drives the journey forward. Meteors are the signposts along the way. Follow them as far as you can. But for now, rest. The journey continues tomorrow. The meteors will wait. The sky holds infinite patience. The universe offers endless opportunities to learn. Sleep comes, consciousness fades. But somewhere always, meteors are falling. Always teaching, always waiting. Always connecting Earth to the cosmos. Always reminding us why we look up. The story of meteor showers never truly ends. Each shower is a chapter in an endless book. Each meteor is a sentence in an infinite story. We've read only a few pages, so many remain. But what we've learned is beautiful, worth sharing, worth knowing. So we share it in documentaries like this. We capture it in research papers and photographs. We teach it to children and curious adults. We preserve it for future generations. Because knowledge matters, understanding matters, wonder matters. The meteor showers teach us this. They've taught it to every human culture that ever existed. They'll teach it to cultures not yet born. The lessons are old, the lessons are new. The lessons are eternal, written in light across the sky. Now sleep, dream of streams and orbits. Dream of ancient comets and modern science. Dream of dust particles older than civilization. Dream of the moment they burst into light. Dream of the sky's infinite capacity for wonder. And when you wake, perhaps you'll look up. Perhaps you'll watch for meteors with new understanding. Perhaps you'll see them differently, knowing their story. Or perhaps you'll simply enjoy their beauty. Both responses are perfect. Both honor what meteors are. The streams continue their ancient dance. The particles follow their orbits. Earth passes through, meteors fall. Science learns, wonder grows. The cycle is eternal, the sky is patient. The meteors are falling now, somewhere always. Over mountains, over oceans, over sleeping cities. Most unseen, some witnessed, all teaching. All connecting us to something larger than ourselves. All reminding us we live in a universe of wonders. Rest in that knowledge. Sleep in that wonder. The universe watches over us all. In falling stars, in flowing streams. In the patient, eternal dance of the cosmos. Good night.